All right, we're going to get started on new material. This is section 12.1. And in it, we're going to be looking at this Diophantine equation, x squared plus y squared equal z squared. Such numbers, x, y, and z, that satisfy this equation are called Pythagorean triples. This is supposed to be a fun, actually, lecture or a fun topic because you're so familiar with it, and it doesn't have any, really very hard material or any arguments. So first we're going to start with some historical remarks concerning the more general Diophantine equation, that is x to the n plus y to the n equal z to the n. All right, so this is an equation in x, y, and z, and n is supposed to be a positive integer bigger than or equal to 1. And with the equation, we are interested in finding solutions for these equations. Of course, for the case n equal to 1, this becomes x plus y equal to z, and this has infinitely many solutions. All right, so that means given x and y, and here we find a z, that is the sum of these two. All right. So this is a very simple case, and in our lecture today, we're going to be concentrating on the this Diophantine equation when n is equal to 2. When n equal to 2, it becomes x squared plus y squared equal z squared, and we're going to find as well this actually has infinitely many solutions. However, when we look at this equation, when n is bigger than or equal to 3, then this equation has actually no solutions. All right, this is what is called Fermat's last theorem, and it has a very, very interesting and lengthy history. All right, and the reason for this is Fermat. He is not a professional mathematician. He is actually an amateur mathematician. His actually profession, he was, a judge. All right, and on the side, he was reading books by Diophantines, and all his work actually were done on or documented in the margins of this book that he was reading. And there are many statements that he made, okay, and some of them, most of them actually are correct and accurate. A lot of them actually written without the proofs, and he did write a few proofs of some of the results. And so all those statements that he made actually were proven, except one. All right, and that one is that this equation x to the n plus y to the n equals z to the n has no integral solution for any n bigger than or equal to 3. So that's why this theorem is referred to as Fermat's last theorem. Actually, it's supposed to be Fermat's last conjecture because it wasn't proven till 1993-94, when the British mathematician Andrew Wiles actually gave a proof, and the proof consisted of about 200 pages of very, very, very hard mathematics. Now, what made this actually this result, all right, interesting for so many mathematicians, both professional, amateurs, and the like, all right, is the statement that actually Fermat wrote on the margin of the Diophantines Arithmetica book. It says, it is impossible to write, that's the way he actually expressed it. It is impossible to write a cube as a sum of 2 cubes, a fourth power as a sum of 2 fourth powers, and in general, any power beyond the second as the sum of similar parts. For this, I have discovered a truly wonderful proof, but the margin is too small to contain it. So in other words, Fermat, actually claims that he knows how to prove this. And many mathematicians and historians of mathematics doubt, Fermat's claim. All right. Then many prizes actually put for solving this problem. Many solutions have been presented, but all has flaws. However, in fact, Fermat did present a proof of the case x to the fourth plus y to the fourth equals z to the fourth, who has no solution. But there's no way you could generalize that for n, which is equal 4 to higher or even 4 to 3. All right. So again, it's a very interesting history about what is called Fermat's last theorem, which is just last century was at the end of last century was actually set. All right, so this is the theoretical remark and the objectives, and I covered with this. So our objective in this lecture is we're going to do the define what we call Pythagorean triple, and a particular type is called primitive Pythagorean triples. And then there is one major theorem in this section that is to find all the Pythagorean triples, which is equivalent to finding all solutions to the Arithmetic equation x squared plus y squared equal to z squared. And then there are a few other minor results concerning Pythagorean triple we're going to prove at the very end. All right, so let's get started by decoding the Pythagorean theorem, which I'm sure every person is familiar with it. Those who like or dislike mathematics, they hear about it, and they can, in some sense, state it. I don't know if you're going to state it precisely or not, but at least they know this equation. So here it is. So we have like a triangle. And the length of the sides are A, B, and the hypotenuse is C, where, of course, A, B, and C are supposed to be positive real numbers. Then we know that A squared plus B squared is equal to C squared. So at least people are actually familiar with this part. So the one important part which we are interested in is the converse of this. And it says that if in a triangle, which is the converse of this statement, in a triangle, if in a triangle with sides A, B, and C, where these are positive real numbers, all right, the sum of the square of the two shorter sides equals the sum of equal the square of the third side, the square of the third side then the triangle is a right triangle. Then the triangle is a right triangle. But of course, we know that the sum of any two sides of a triangle is going to be bigger than any third side. So we're taking the two sides that are shorter, so the third is going to be bigger than at least two. All right. Now, what does this actually say? So in other words, we are interested in in determining in another triangle with sides A, B, and C. So in this case, we need to determine, for basically for what values. So this is equivalent to saying there, okay? To find all possible A, B, and C such that A squared, let's assume that the A and the B are actually the shorter sides, is equal to C squared, where in terms of triangles, the A and the B and the C are positive real. Now, in number theory, we are interested in integral solutions. Okay? So, in number theory, we are interested in integral solutions of integral solution. Let me just actually into this state. So in other words, we are interested in finding all integers or positive integers x, y, and z that satisfy this equation. X squared plus y squared equals z squared. Now we're going to describe, such triple of numbers that satisfy this equation as a Pythagorean triple. All right? And then we're going to specify, a different kind of Pythagorean triple, which we call it primitive. All right? Pythagorean triple. So really, this is just strictly where, this question comes in. And let's start with formally defining. So here's the definition. We have a triple a Pythagorean triple f x squared plus y squared is equal to z squared. We are all familiar with some Pythagorean triples. We take 3, 4, 5. Then we know that 3 squared, 9, plus 4 squared, 16, is equal to 25. And in fact, if you multiply each member of this Pythagorean triple by a number, it's 6, 8, and 12. This is another Pythagorean triple. All right? And so you can see that there are infinitely many Pythagorean triples. Another example is 12, 13, 5, 12, and 13. Let me actually go like this. 5, 12, and 13. And there are many, many more. All right? Now, a Pythagorean triple, let me actually make this following statement. Here's the remark. If x, y, z is a Pythagorean triple, what am I saying here? Pythagorean. And b any positive integer, all right, then dx, dy, dz is also a Pythagorean triple. And this is not very hard to see, because if you take dx squared dy squared, this is equal d squared x squared plus y squared, and this is d squared z squared, and this is equal dz squared. All right. What does this mean? This means that if we know a Pythagorean triple, then we can generate infinitely many Pythagorean triples just by simply multiplying, this Pythagorean triple by any positive number. So we need to consider those Pythagorean triples that they are not multiple. Okay, there is not one multiple of a specific number. Such Pythagorean triples are called primitive. A Pythagorean triple x, y, z is called a primitive Pythagorean triple if the greatest common divisor of x, y, and z is equal 1. So there are there is no common factor actually for this, or the greatest common divisor is equal to 1. All right. So our objective, as I said, the main theorem of this section is to find all the Pythagorean triples. Now, since if I can find, okay, the primitive Pythagorean triple, then I can multiply these by different positive numbers and obtain all the Pythagorean triples. All right? So in other words, it is only sufficient to find only the primitive, all right, the Pythagorean triple. In fact, Pythagoras, or Pythagoras, gave a formula that generates infinitely many Pythagorean triples namely this. Take x equal to n plus 1, y equal to n squared plus 2n, and z is equal to n squared plus 2n plus 1, where n is a positive integer. All right? However, and which is not very hard to check, okay? It is easy to check that x squared plus y squared for these values is equal z squared for every n bigger than or equal to 0. Just a matter of squaring and comparing the two sides. However, not all Pythagorean triples are generated or can be expressed generated by these formulas, by the formula that Pythagoras gave. For example, if you look at the Pythagorean triple, 6, 8, and 10 cannot be actually generated by that. And it's very easy to see because if you set this one is equal to n plus 1 actually, and then from here you will find that 2n is equal to 5. And this, there is no integer that satisfies this, or if you try to actually set this is equal to 6, and similarly, then this is going to be 8, and you're going to run to the same problem. All right? So in other words, not all Pythagorean triples are generated by this. In fact, we know how to generate infinity, Pythagorean triple just using 1. All right. So now it's if I have a Pythagorean triple, here's another remark. If x, y, z is a Pythagorean triple, and the greatest common divisor of x, y, z is equal to d, may not equal to 1, then there exists a primitive Pythagorean triple let's call it x1, y1, z1, such that x, y, z is equal d x1, d y1, d0. Now, what we obtain by multiplying the primitive Pythagorean triple by d, which is the greatest common divisor. Now, this is very simple to see. All right. Now we have d divides x, d divides y, d divides z, and which we can then say that x can be written as dx1, y equals dy1, and z is equal d0. And we also know that the greatest common divisor of x1, y1, z1, this is going to be equal to 1. All right, and it's not very hard to see that x squared plus y squared equal to z squared. All right. If I wanted to say that, sorry, x1 squared. So from here, we have, since x is squared, which is, it's kind of right there, z squared, this is equivalent to saying d squared x1 squared plus d squared y1 squared equal d squared z1. And upon dividing by d squared, then we obtain that x1 squared plus y1 squared equals z1. So this means that x1, y1, and z1 is a primitive Pythagorean triple. All right. So what does this remark again imply? That any Pythagorean triple, all right, we can actually obtain it from a primitive Pythagorean triple by just multiplying the the primitive Pythagorean triple by the greatest common divisor. All right. So in other words, our objective is to only find all the primitive Pythagorean triples. So in other words, to find all Pythagorean triples, we need to just find the primitive Pythagorean triples. All right. So, and to do this, we're going to start with a few lemmas, okay, to pave the way to the central theorem of this section. All right, so here's a lemma. It says that if x, y, z is a primitive Pythagorean triple, then any two of these integers are relatively prime. Then the greatest common divisor of x, y is equal 1. Greatest common divisor of x, z is equal 1. And greatest common divisor of y and z is equal to. All right, here's the proof. So let's assume that we have xy x, y, z is a primitive Pythagorean triple. And assume that, I don't know if you're going to do it by contradiction. Assume that the greatest common divisor of x and y is equal to b bigger than 1. All right? Then I'm going to take a prime factor of d. Okay. Let E be a prime factor of D. So this means that E divides D. And now we know that we have also D divides X and D divides Y. These divisibilities implies that P divides X and P divides Y. And also P divides a combination of these. So this implies P divides X squared plus Y squared. But this is equal to Z squared. So this implies that P divides Z squared, but since P is a prime, then this means P must divide Z. Well, this implies P is a common factor of X, Y, and Z. And it is bigger than 1, so this of course is a contradiction because X, Y, and Z are, together they are prime. It means as a whole, the greatest common divisor is equal to 1. All right? Similarly, we can prove, of course, the other two in a very similar way. All right. Now, the next lemma, we're going to look at the parity of X, Y, and Z. In other words, from even up, what kind of possibilities of even and odd they may actually have. All right? So the previous lemma, actually, it's not stated in the book, but it's nice to have. And here's another lemma. I call this is lemma 1. And it says that, again, if x, y, z is a primitive Pythagorean triple, then either x is even and y is odd, or x is odd and y is even. Sometimes we express, this by saying this is equivalent to saying that x is not congruent to y mod 2. So two integers that they have different parities, means they are not congruent to each other mod. All right? Let's go with the proof. So we have a Pythagorean triple. All right? Now, YZ be a primitive Pythagorean triple. We know that from the previous lemma. The greatest common divisor of any two of them, let's say x and y, is equal to 1. And this implies that we cannot have x and y cannot be both even. This implies x and y cannot be both even. So otherwise, then they would have the 2 as a common factor. Also, x and y cannot be both up. Be both odd. And the reason for if x is odd, 2k plus 1, and y is equal to 2k prime plus 1, then let's look at x squared plus y squared is equal 4k squared plus 4k plus 1 plus 4k prime squared plus 4k prime plus 4. And altogether, this gives me 4 with k squared plus k prime squared plus k prime plus 2. And this becomes congruent to 2 mod 4. But we have this x squared plus y squared is a square. This is equal to z squared. So that itself implies z squared is going to be congruent to 2 mod 4. This is a contradiction since n squared is congruent to 0 or 1 mod 4. Right? So you cannot have a square congruent to 2. All right? All right, so therefore, either x is even and y is odd, or of course vice versa. And that would be that. All right, we need one more lemma, and this lemma actually uses the fundamental theorem of arithmetic. And the content of the lemma is going to be a little more general than what we need. Is basically what we need to show, to have, is if the product of two integers is a square, then the integers themselves in this product are squares. All right? So here is the lemma in a little more general. This is true for other higher powers of actually if a product is a cube or a fourth root or a fourth exponent or another integer in the original two numbers that are multiplied to give that are themselves are third power or fourth power and so on. So this is lemma 2, and it reads this. If A and B are, they need to be relatively prime, are two relatively prime integers, and their product equal the nth power of another number c, where c is an integer, of course, and n bigger than or equal to 1, then A and B are nth powers are both nth powers are nth powers. That is, there exist integers A1 and B1 such that A is the nth power of A1 and B is the nth power of B1. All right. Let's go ahead and prove this. And again, as I said, we're going to be using the fundamental theorem of arithmetic, which means we're going to look at the prime factorization of A and B and C and try to compare them once we put them into the equation. All right? So we're going to let A equal P1, K1, P2, K2. up to PR KR, and B equal, I want to be using continuation of these primes. I want to make this as R, BR1 plus 1, K R plus 1, BR plus 2, K R plus 2, and so up to B sub S to the K to the S. All right? So let these be the prime factorization of A and B. Now, since these are relatively prime, since let's common divisor AB equals to 1, this implies all these primes, Pi does not equal B sub j for every I does not equal to j. All right? And I and the j runs through, you know, the I runs through 1 to R, and the j runs through the R plus 1 to S. Otherwise, they are not equal to each other. All right, now we're going to let C equal the Q1, let me see in here, L1, the Q2, L2, up to Q M, L sub M, be the prime factorization of C. Now, I don't know anything about the relationship between the Q's and the P's in here. We cannot say these are actually different, distinct. But let's look at the equation, since now AB equal C to the N is equivalent to saying that P1, K1, P2, K2 up to PR K sub R, BR plus 1, KR plus 1, BS K sub S is equal to Q1 N L1, Q2 N L2 up to Q sub M N L sub M. Now, by the fundamental theorem of arithmetic and the uniqueness of the primes in the two sides of this equation, the primes in the two sides of the above equation this means that for every Pi there exists a C sub j, a Q sub j, such that the P sub I is the K sub I, all right, is equal to Q sub j. And also the exponent, because all of these are different, these are distinct, the p's and this side. So and the exponent must also equal to each other. So this is n L sub j. All right. So for every p sub I, we have this matches with the q, and also the exponent are the same. So which means that the k sub I must actually is equal to the n L sub j. And this makes the L sub j is equal to Q sub I divided by n. Now, we're going to let A1 is equal P1 to K1 over n, B2 K2 over n, up to P sub R, KR over n, and B1 is equal PR plus 1 and KR plus 1 over n up to P sub S KS plus KS, over n. All right, then clearly we have when you raise this to the power of n, so this implies A1 to the n is equal all of these p's KR over n to the n, and this is of course equal P1 K1 up to PR KR, and this is equal to A, and P to the power n will be the other primes, KR plus 1 over n, S KS over n to the n, and this is going to equal. All right. In particular, we're going to be using again this lemma for AB is equal a square of another number, and we're going to use this fact that the A and the B are themselves a square. All right. All right, now we're going to give a complete description, all right, of all the primitive Pythagorean triple. This is given on by Theorem 12.1. I want to state this theorem in two different ways. They are equivalent, okay? One, it proves that like there's an if and only if, and the other one is just give the sort of the description. All right, all the solutions of this equation, x squared plus y squared equal z squared, satisfy the following conditions. And these are the conditions to make these solutions are actually primitive Pythagorean triples. Then we have the greatest common divisor of x, y, z is equal to 1. We're going to remember that we said that the x and the y cannot have the same parity. It means one is even and the other is odd, or the other way around. So we're going to go with the x being even. So we're going to have the 2 divided by x. And of course, the x, y, and z are all positive integers. And we have the x is equal to st, y equal s squared minus t squared, and z equal s squared plus t squared, where the s is a positive integer bigger than t, and so are relatively prime. And they don't have the same parity. So this one is not congruent to 3 mod. Mod 2. T. Alright. So this is one way to state the theorem, and this is equivalent to this statement. All right? The triple x, y, z are positive integers is a primitive Pythagorean triple with x being taken even if and only if there are relatively prime positive integers s and t where s bigger than t, s is not congruent to t mod 2, means either one of the two situations, s is even, t is odd, or the other way around, such that x is equal to st, y equal s squared minus t squared, and z is equal to s squared plus t squared. Well, in the second form, what we are saying that this triple is going to be a solution for the Burton equation x squared plus y squared equals z squared, which is satisfied being a primitive. All right, if and only if we can find relatively prime integer s and t that satisfy these conditions and give these values for x, y, and z. All right, so we're going to prove two things. First, we're going to assume that we have a Pythagorean triple. Then we're going to find the S and the T, which satisfy all these properties. All right? And conversely, given this X, or given this S and T, then we're going to show that the X, Y, and Z, in fact, form a Pythagorean triple. And that is a primitive. So let's start with this direction in the proof. On this way. So let's assume that x, y, z is a primitive Pythagorean triple. And we need to show the existence of S and T. Okay? To show there exists S and T that satisfy the conditions given in the theorem. Properties or conditions as given by the theorem. But first of all, we know that by lemma 1, we know that either x is even and y is odd, or vice versa. So let's assume that this is what we have. So in other words, assume that the x is even and y is odd. I claim that also z must be even. Then z is odd. So then z must be odd, and hence we have the z plus y and z minus y are both even. Okay, the difference between two odds or the sum of two odds is even. So this implies that z plus y is equal to v, let's say, and z minus y is equal to u for some integers v and u. Now let's look at this equation we have, because this is a Pythagorean triple. So this one is, we have x squared plus y squared is equal to z squared. Or this implies that x squared equal z squared minus y squared. And this is equal z minus y, z plus y. And this is equal to 4 uv. And then we can write this as the following. So this implies that x over 2 squared is equal to z minus y over 2 z plus y over 2, and this is just equal u. In other words, if we divide both sides by 4 and rewrite this equation like this. So this implies that uv is a square. Of course, here of x over 2. Then by the second level, means that u and v. One other thing we need to show. These are actually relatively prime. Okay, so another thing I want to show, then we can use the lab. I claim that the greatest common divisor of uv is equal to 1. And to prove this, again we're going to do it by contradiction. And assume that the greatest common divisor of uv is equal d bigger than 1. Then what we have in here, we have, this implies d is going to divide u and d divides v. Then it divides combination of these. It's going to take u minus v, and d divides u plus v. Well, let's see what is what we have in here. Now remember that we have z minus y is equal to 2u, and we have z plus y is equal to v. I think this is what we have in here. Let me make sure that the sum is 2v. Yeah. Then if I add these together, this implies that 2z is equal to 2u plus 2v, which implies that z is equal to u plus v. And if I subtract these, I'm going to come up with actually y. So I'm going to subtract the the top one from the bottom one. So this one's going to give me a, let me see it here. So if I subtract this one minus, so the z cancels, so I come up with 2y is equal v minus u. Let me do it the other way around, actually. No, that's fine. Let me have this one is 2v minus 2u, and this implies y is equal to v minus u. Now, with these two divisibilities, this means that d is going to divide negative y, and d is going to divide z. But this means that d divides the greatest common divisor of y and z. But this is a contradiction since greatest common divisor of y and z is equal to 1, because this is a primitive Pythagorean triple. So this is not the case. So in other words, yes, we have the greatest common divisor of u and v is equal to 1. Now we can apply lemma 2. So by lemma 2, since u v is x over 2 squared and greatest common divisor of u v equal 1, this implies u itself is a square. And I want to choose for it actually t squared. And v is a square, and I want to take for it s squared for some integers t and s. And of course, we take them to be positive integers. All right, we take these are some positives, which is a positive. All right, now let's see what we have in here. Remember that we have z minus y. This one is equal to u plus v. This one is equal to 2u. And then we have z plus y is equal to v. So when we substitute in for this becomes 2t squared, and this becomes 2s squared. And again, we can solve for both. Is actually 0y. So when we add these, we get 2z is equal to s squared plus 2t squared. And this gives me what z should be equal to, s squared plus t squared. Similarly, when we subtract, and we could find the y. And this would also, of course, equal to t squared minus, we actually have this is v minus u, okay? And this is s squared minus t squared. And then from this equation, that x squared, let me have more space in there. And also we have the x squared, which is equal z squared minus y squared. And this is equal to z minus y, z plus y. And this is equal to 2u and 2v. And which make the, and again, in terms of t, 2s squared, 2u is t squared. And altogether gives me 4 s squared t squared, and this gives you what x is. All right, so we obtained that we proved the existence, all right, of s and t, and which give me the different values of x, y, and z. We only need to show now that the s and the t are relatively prime, all right? And the s and the t, they don't have the same parity. They are not congruent to mod 2. All right, so here's the claim. The greatest common divisor of s and t is in fact equal to 1. Again, assume that this is equal to d. And this implies, of course, that d divides s. And of course, d divides t. So this implies d divides s plus t. But when you add s and t, actually, you find this is z. And again, you're going to find that d divides s minus t. And this happens to actually equal to x. And this means that d divides the greatest common divisor of x and z, which is equal to 1. So which makes actually d should be equal to 1. All right? Equal to 1, or we could do by adequate choice. All right. The last thing we need to do is we're going to go the other way around. So we need to go conversely. And this is actually the easier way. Let's go actually this way. So we're going to let s and t be integers, positive integers. The two relatively prime positive integers. And x is equal to st, y is equal s squared minus t squared, and z is equal to s squared plus t squared. Where also we have one other condition, s is not congruent to t mod. So in other words, we have exactly these values of x and y and t, and I want to show that x, y, and z is a Pythagorean triple. So the claim here is x, y, z is a primitive Pythagorean triple. So the first thing we want to do is to show that, is it true that x squared plus y squared is equal to z squared. And this is just a matter of basic algebra, means you want to see if you square this minus t squared, is this going to equal to s squared plus t squared squared. So I leave that for you. It's very straightforward. Computation, either you start with the left side or right side and get it to equal to the other side. Then we're going to show that other thing. We need to show that the greatest common divisor of x, y, z is equal to. And again, to do this, we let the greatest common divisor equal to d, and let b be a prime divisor of d, and try to find the contradiction. All right? All right. Once again, we have d being dividing all of these means that the prime p is going to be dividing, okay, so d divides x, y, z, and b divides d, maybe here, implies that b is going to divide x, y, and z, and this makes the b divides the greatest common divisor of d. Third word from here, the way we took the the x, y, and z. Remember, this was odd. All right, and p divides y implies p cannot equal to 2. And now we have so we have p divides y and p divides z. Let's use this one, and this makes this p divides their combination. And if you do the combination in the end, it gives you 2s squared. And again, this means since p is not equal to 2, then p divides s. All right. Similarly, we where the divisibility that make p divides t, and we this is the contradiction. All right. Also from these two, we can say that p divides z minus y, and z minus y is equal to 2t squared. And then this forces b to divide t. And this is a contradiction since greatest common divisor of s and t is equal. So that not bad. All right. So this is it. This is the major theorem. This gives us to generate all basically the Pythagorean triples. All what we need is to consider all values of s and t that they are relatively prime to each other, all right, and they have different parity, all right, and then x is 2st and the y is equal to s squared minus t squared, of course. I think the s is bigger than t in here, and then the z is s squared plus t squared. So by considering all S, T are positive and S bigger than T, greatest common divisor, and they are not the same parity, mod 2. By considering all possible values of S and T that satisfy all these conditions, all right, then, and you substitute for these for X, Y, and Z, you come up with a primitive Pythagorean triple. And then you could multiply that primitive Pythagorean triple by a positive number, then you get all other Pythagorean triples that has this is as their primitive one. All right? Of course, you don't want to generate all of them because there are so many, right? All right, here is another property, I don't know if you're familiar with, is that in any Pythagorean triple, one of the integers actually, only one, either the X or the Y is divisible by 3. All right? So this is a corollary that follows from the theorem. It says that if X, Y, Z is a primitive Pythagorean triple, then exactly one of the integers X or Y is divisible or multiple by 3. All right. We know that X is equal to ST and Y equal S squared minus T squared for some S bigger than T bigger than 0 and satisfy all other properties, okay, of the S and the T as given by the theorem. And of course, one of these is also the greatest common divisor. ST is equal to 1 and the parity. All right, now, if we have 3 divides S or 3 divides T, then the 3 will divide X. And we'll be almost done if we can show that the 3 is not going to divide Y. Okay, because we need to show this exactly. All right? Then we would be done. If we show the 3 does not divide Y. Well, let's see. Now we know that since the greatest common divisor of S and T is equal to 1, then the 3 cannot divide both of these. Then the 3 cannot divide both S and T. In other words, this 3 divides S or 3 divides T, it's going to be one of them, not both of them. Well, let's assume that 3 divides S let's assume that the 3 divides S. Now, to show that 3 does not divide Y, okay, so I'm going to do it by contradiction, all right, which means we can assume this one and assume that the 3 divides Y. Well, this implies that the 3 is going to divide combination of these. So I will multiply this by S, and that is by -1, so it becomes S squared minus Y. And which means this is T squared, because this is square minus 1, which means that 3 divides T squared. But the 3 is a prime, so this means 3 is going to divide T, and this, of course, is a contradiction. So in other words, it can't. All right? So it means this is it. So if a 3 divides S or 3 divides T, then 3 divides only X. All right? Now, this is going to be the other way around. It doesn't divide. Now, let's assume that 3 does not divide S and the 3 does not divide T. So this means that you take the greatest common divisor over 3 and with its prime and S. So this is equal to 1. And the greatest common divisor of 3 and T is equal to 1. Now let's apply Fermat's theorem. We have S 3 minus 1 squared is going to be congruent to 1 mod 3. And we have also T squared congruent to 1 mod 3. Which means that the Y, which is equal S squared minus T squared, is congruent to 0 mod 3. And which makes this Y actually is going to divide the 3. Right? And that's it. So if in other words, if both of them does not divide T, then the Y actually divides, 3 divides Y. I'm sorry, not Y divides 3. Or, and of course, not very hard also to see that 3 will not divide actually X. Because if it does, then it's going to divide either, S or T. Because remember, this one is 2S. So it doesn't divide 2, so it's going to either divide S or 2, which of course contradicts this. All right, one last interesting fact that is, if you take a right triangle and you inscribe in it a circle, then the radius of the circle must be an integer, integral value. So this is the last theorem for section theorem 12.2. It says that the radius describe circle of a Pythagorean triangle. Means a triangle that all its sides are integral values. We say Pythagorean right triangle, okay, just for double emphasis. Is always an integer. And well, this is the only picture in this book, or a figure rather. All right, so we have a right triangle in here, and we are inscribing, I don't know if I can do a good job, a circle. It's not perfect, but it's in here. Then the radius of this circle, all right, R, is going to be integer. And the idea is this, let's call the sides of this is X, Y, Z. And let me call this is A, B, C. Like this. The idea of the proof is to write the area of the triangle in two different ways. One way is to have it as the triangle with base is y, the height is x, and this is equal 1/2 xy. And another way is to divide this is into three triangles. And when we do this one, we're going to connect these two. And then we're going to do this. Then find the area of, let me call this is O, all right? And also the area is equal to the area of the triangle. Sum of the areas of the three triangles. Three triangles. AOB, AOC, and BOC. Okay, so let's see each one of these. So this is going to be 1/2. The AOB, we know that this is R, so it is going to be 1/2 XR. And then the AOC, AOC is going to be 1/2 Z times R. And then 1/2 YR. And when I equate these to each other, these are the same area. And just a little bit of algebra, we should get what we're looking for. So we have 1/2 XY equals 1/2. We can take also actually a factor of R out in X plus Y plus Z. Cancel this out. And we get R, that's what we would like to show. It's an integer. Is going to be xy over x plus y plus z. Now we need to use the theorem, which give us what are the sides are. Now remember the theorem give us primitive Pythagorean triple. So to get it for a triangle, then we're going to take this and multiply it by some k. So in other words, we want to take the primitive and multiply it by a number to come up with, you know, what it's supposed to be for another primitive Pythagorean triple. And then we have the y, which is equal s squared minus d squared times k. And z is equal s squared plus d squared k. So these are the length of these sides for an integer k bigger than or equal to 1. All right, now when we substitute this in here and do very basic algebra, we get 2stk multiplied by s squared minus d squared k, and put these in the denominator, s squared minus d squared k plus s squared d squared k. Let's see how well terms it will cancel out from the denominator. So we have s squared, the t squared cancel out, all right, in here. So we end up with s squared. Let me take a k out. Then we have s squared, 2s squared. And then we're going to have 2st. All right. And in the numerator, we're going to have a k squared, and then 2st times s minus t, s plus t. Oh, no. And let's take an s out in here, or 2s also. So this becomes s plus t, I think, right? And I'm going to see that the 2s cancel out, k cancel out, s plus t cancel out, and we end up with k t s minus t. And definitely this is, it's a positive integer. All right, because all the k, s, and t are integers. All right, so this is it. Yeah, I think that's what I have. All right. I hope, you know, as I said, this is kind of a fun topic. I will make it a little more interesting, I don't know. But with the time being running out, we have to, so I've done it the way I've done it, all right? So I'm going to stop right here. One more lecture to go, and we'll be at the end, all right?